Thanks a lot. Okay, well, it's a pleasure to be here. My name is David Benjamin. I'm Director of Research at Autodesk and also the head of a studio within Autodesk Research called The Living. And today, what we want to talk about is a kind of applied research project that was a collaboration between Autodesk and Airbus. And this project, as you've already heard a little bit about, involved generative design and additive manufacturing. Generative design basically means creating high-level goals and constraints for a certain design that you're interested in achieving, and then using the power of computation to automatically create many, many design options, explore a very wide design space, and then come up with results that are both high-performing and unexpected. Additive manufacturing, of course, everyone here knows what that's about, and the kind of goal of the project, the high-level goal, was to achieve lower weight in airplanes and airplane parts. And I think this fact on the screen is key to why we are doing this. It basically means that 1 kilogram of weight savings in parts translates almost 100-fold or more than 100-fold to savings in fuel, and this also translates to lower costs and lower carbon emissions. So in this project, we aim to bring together both generative design and additive manufacturing to explore creating new lighter weight airplanes and airplane parts with the goal of creating more sustainable air travel. So with this as the kind of aspiration of the project, we kind of set out to explore a new approach to both design and manufacture of these new lighter weight planes. But we started with a single component called a partition. The partition is the dividing wall between the cabin and the galley in a plane. It's a part that you've seen hundreds of times when you've been on flights. And like all parts in the plane, it must undergo intensive requirements for certification, including a 16G dynamic test, a kind of crash test. And you can see it here in slow motion. And this shows the kind of extreme loads, extreme structural loads that parts in the cabin need to withstand. It shows the kind of high level of structural performance in this part. And although this part may look kind of standard, mundane, even a little bit forgettable, this is actually a very difficult part to design in a lightweight way using traditional manufacturing methods. It has a few aspects that make it difficult to design. First of all, it can only be about 1 inch thick, about 2.5 centimeters thick. Then it can only attach to the airplane's main structure, the fuselage, at 4 points, 2 above and 2 below. Then, on top of that, it needs to hold the fold-down cabin attendant seat that you saw in the crash test video. And that's an asymmetrical load. The cabin attendant seat can't touch the ground. It needs to hang off of the partition, and it's hanging, creating an uneven load, an asymmetrical load on the partition. And just when you think you may know how to kind of sketch a design from engineering rules of thumb with some cross-bracing, you find out that this smaller shape that's inset here, called a stretcher flap, needs to be removable from the component, which creates additional challenges to traditional engineering. And that's because if someone gets injured in the seating area of the plane, you need to be able to put the person on a stretcher, bring them around the corner and out the door, and this in some cases requires literally removing a part of that wall, a part of that component. So in other words, we picked this part because it's a challenge to design in a lightweight way. And it's at this point that in the generative design process, our design studio turned to an idea of borrowing geometry and logic from nature. More specifically, we looked at the way that Physarum grows in complex networks that are efficient and redundant. So this is a living organism that starts in a central point, grows out in this branching network to get sources of food, which are the dots, and it creates these networks that are efficient and redundant. They're efficient in that they're using a small amount of lines to connect the dots, and they're redundant in that if one of the lines gets damaged, the system as a whole can route around the problem and still more or less keep the dots connected. So in our computational workflow, we created an algorithm that models the logic of Physarum growth and that creates complex networks that are both efficient and redundant. And on top of that, we can create many different efficient networks by varying a few input parameters and evolve different designs that meet our desired criteria. So here we use the power of computer automation to generate, evaluate, and evolve literally tens of thousands of design options. This kind of process of artificial evolution in the computer allows us to explore a wide set of possible designs. Some of them are unusual, many of them are very complex. A lot of them extend beyond what a typical engineer would sketch. And not all of them are useful, but some of them are actually very efficient at solving the problem. Here's a different view of the generative design process. Each dot on the graph is a design option, so you can see that we're exploring many, many different designs. Then we can use some aspects of visualization and other algorithms to sort the designs. We can color code them by the type of design solution they are. We can plot them on a graph where the x-axis is weight. We want to minimize that. The y-axis is displacement under structural load. We also want to minimize that, so we want to be at the kind of 0, 0 point on the graph. We can't quite get to 0, 0, but we can get a trade-off curve of weight and strength and mathematically determine some of the best options. But it's important to note that there are many different ways to solve the problem, and this process allows us to discover some ways that we wouldn't have discovered otherwise. Then, just like nature, we can run this process at multiple scales. So the first scale is what I already described. We take the surface of the partition and we create an efficient network of crisscrossing black lines shown in the center, which is basically like cross-bracing for the partition. But then we can basically create every segment of black line from the center image out of, in turn, hundreds of tiny red lines that we call microlattice bars. And in fact, in our final partition, we have literally 60,000 microlattice bars, each one sized according to the amount of structural performance that it needs to perform. So in order to translate from the digital process to the physical manufacturing, we had to break down the problem into smaller pieces again. So here we're testing a single rod as a prototype component. We test it in the computer with digital simulation, and we do some corresponding physical tests, making actual parts out of the actual materials with additive manufacturing and testing them under load. In one of our more complex tests shown here, we first did the bottom image, which is simulate where we think that this complex lattice will have its most weak point under its structural load. And if you look closely within the red oval, you can see an area that has a little bit of green and red. Those are the areas of the the weakest structural performance under this particular load. Then we did the corresponding physical test, and if you look closely, you can see that the component broke exactly where we thought it would break, where the component as a whole was the weakest. And with this level of kind of confidence in our overall design approach and in the correspondence between the digital world of design and simulation and the physical world of manufacturing, we were ready to turn to making the full-scale real part.
Perfect. So, yeah. We've been learning a lot about 3D printing in that time, so we started with this project in 2012 around, and we saw very quickly we cannot produce everything in one shot. So we had to break this down to make it fit into the tiny build chambers of the 3D printers we had at that time. The largest printer we were using was an M400 from EOS, which allowed us to create bigger components. So you can see here in this video how the build platform is getting disassembled from the printer. Yeah, but this is not the end. We, as you know, the process of 3D printing is pretty tricky, especially when it comes to qualified parts. What you can see here on this picture is the rough surface. One of the biggest lessons learned is the setup of requirements in such kind of project. So for aircraft components, you never would accept this type of surface quality as it involves notching, yeah? And you want to avoid notching when you have parts that have to resist high strengths. However, in an aircraft cabin, we do not have these fatigue requirements that also involve notching, so we were able to accept this type of surface, so take care of your requirements in the end of the day. What we also did was to create a very dense build platform to increase the efficiency of the parts. This was also done at the first time at Airbus. In total, we had to handle 7 build jobs and printed with a material that is called scalm alloy. Scalm alloy is an aluminum, magnesium, scandium alloy, and this is made for 3D printing. And the amazing thing about scalm alloy is, and the reason why we just can use it for 3D printing, you need very high cooling rates in your build chamber to allow the scandium to make a connection with the magnesium and aluminum. So if you have very low cool rates, like in a casting process, you don't get the strength into the part. And this is why 3D printing with scalm alloy was one of the key success factors here in the end of the day. Yeah, as I said, we had 7 build chambers and in total 116 parts to handle, plus 40 titanium connectors. So you can see them here. The basic principle was that we put all the complexity into the so-called knots, where we have the interconnection of a lot of structure, and these knots have been extended by the so-called rods just to make larger parts, and we connected them with these dedicated connectors in the end of the day. The part has a height of more than 2 meters and a width of 1,400 millimeters and a thickness of 1 inch only. I believe still today it's the biggest 3D printed component from metal that we have at Airbus so far. Here you can see the animation of the FE model in the end of the day, where you can see in terms of this 16G acceleration, you have still some concentrations of stress here, but that was completely acceptable. And that was the day when we had the static test. So this is not the 16G test. You perform a static test before, where we had to show that the partition can resist approximately 13G of loads. So, and you can see how it's bending and that was really exciting because you can see the deflection of the part goes back in the end of the day. Also thanks to Skalmalloy, which has an elongation to rupture of 16%, what we have measured, which is pretty much for 3D printed metal components. So in the end of the day, we were able to bring the weight down by 45%. And one thing that I'd like to mention here, this is an innovation project. Yeah, we didn't make it into the airplane. I will explain this later on. But when you perform such a kind of project where you have a new technology, a new design approach, you are able to set your supplier base under pressure because they have to involve and innovate even further to be part of the game. So, and to give a statement that we have a prototype that resists the required forces and that has approximately half of the weight, this is a word in the aviation industry. We also did a life cycle assessment for our component, and assuming that we can recycle the metal parts from the partition, let's say by 50%, we are 3 times better than the standard part. This is due to the fact that we simply have weight reduction and that we have that we need less energy to fly this in an airplane. But we were able to show that we have a real environmental benefit here in the end of the day. Let's talk a little bit about industrialization. We were thinking about to build this part in-house, so we made a design for a factory from scratch. You can see a lot of 3D printers here. We imagined to have large printers like the X1000R from Concept Laser, for instance, in order to print 60 partitions per month. Yeah? So, and what we saw as well is that there is a very nasty process behind it. So this here is the entire process to build a qualified partition at Airbus. And even if you print this out on a large paper, you still have very tiny letters to read, and you probably need glasses to do this. So this is actually what happens in the 3D printer by itself. The rest of this is data handling and it's post-processing of the part. And that was a very bloody learning curve we had when we saw that only 1/3 of the cost of a 3D printed part occur in the printing process itself. The rest, 2/3 of it, is post-production, post-processing, milling, surface polishing, hot isostatic pressing, CT scans, and so on. And believe me, when you talk to Airbus engineers and there's a method that we can add to 3D printing to raise the quality and to raise the cost, of course, they will do it. Yeah? They want to have 100% safe parts in the end of the day. This is actually what happens in the laser. And this is actually what your management understands when they talk about 3D printing. Yeah? It's just you have a file, you press start, and the rest is magic and happens by itself. Honestly, I have to say, and this is what our head of additive manufacturing at Airbus said, if you want to have a cheap part, go back to machining. Yeah? Today, we are still struggling to get the business case right for tiny parts. Yeah? Because milling parts are also expensive because there's a big margin inside, but when we try to come to the price of a milled part with a 3D printed part, they will decrease the price again, and so this is a cat and mice game. So at a certain point, we have decided to move away from direct 3D printing and adjust a little bit our approach. And we saw a big benefit in printing a mold and to go back to casting and enable traditional technologies to become or to have a better performance in the end of the day. And so we started again with our single rods that we adjusted a little bit better for casting processes, and we also were able to adjust our design strategy a little bit. So what you can see here is at the right-hand side you have a FE representation of the part, and at the left-hand side you can see how an algorithm is increasing the thickness of the single bars, and you can see that at the right-hand side, the red colors disappear, and that the structural performance is becoming better. So there's a huge need for us to dive into these topics of designing algorithms in a generative design process and to use additive manufacturing directly or indirectly to create better parts. And finally, this was one of the early stages of the Stretcher Lab. You can see we do not have a lattice structure anymore. We just changed the design philosophy, adjusted this towards casting. And this is what we are doing at the moment. So we hope to get this prototype by December. So this is very fresh in the end of the day. And we hope that we then can bring additive manufacturing to the next level in order to, of course, our engineering dream is to have larger 3D printed structures and optimized structures in the future to make the aviation industry really sustainable. Yeah, that was our presentation. Thank you so much for your attention.
Thank you very much, both of you. Appreciate that. Does anyone have any questions regarding this for... Yes, sir, right there.
You mentioned very briefly that you were also using CT scanning as a part of the process. Mm-hmm. What are you actually doing with CT scanning? What is the purpose with this?
Check the porosity, check for internal cracks, and so on.
So it's for analysis, it's not
for analysis, yes.
Not metrology.
Yes, exactly. Yeah.
Okay, thank you.
Any other questions at all for the guys here while we've got them on stage? And one thing I wanted to actually ask is that, obviously this is early stages of this sort of project here. There you've got the partition walls. What are the next stages? Which parts are you looking at going on from next? I mean, like, it's not sexy, but it's important. What's next on the list?
Well, we've conducted even further projects with David's team. So we've been looking at the so-called leading edge of the vertical tailplane of an airplane. So this is the upright wing. And the leading edge has to be very stable as it has to resist a bird strike. So we applied generative design and additive manufacturing for that, with a vision that when we make a structural component, this also can resist higher loads, but it also can function like an antenna. Yeah? So we can integrate even further functionalities into that in order to remove parts from the airplane to make it lighter again. Yeah? So that was one case study we did. However, we are looking very much at the different additive manufacturing technologies, look very much at the industrial performance of them, and if we get materials that are certifiable. And this happens very much in the cabin at the moment. Regarding the primary structure, we have to see. So there's still a long way to go to automate the post-production process to make it economically reliable. And this is our first focus at the moment before we look at other things.
Excellent. Thank you very much indeed, both of you. Thanks very much indeed, everyone. Cheers.